Let's continue on functions and their graphs. Then we'll move on to section 1.7 on the transformation of the functions. So we're going to have a horizontal shift, vertical shift. There are four types of horizontal shift, four types of transformation. Vertical shift, and refraction. We'll call this rigid transformation. Rigid. Because the shape of the graph does not change. The only thing changes the position of the graph. Rigid. Transformation. The fourth one is non-rigid transformation. It's like a distortion. Distortion is the non-rigid transformation. So we're going to learn use the vertical horizontal shift to sketch the graph of the functions. Use refraction, sketch the graph of functions, and use non-rigid transformation to sketch the graph of functions. First of all, let's take a look at horizontal shift, the vertical shift. So it's generally called shifting graphs. Many functions have graphs that are transformation of the parent graphs. For example, h of x equal x squared plus 2 come from the parent function f of x equal to x squared. We call that second degree polynomial function, a square function. So going from f of x to g of x to h of x here, we're shifting the graph upward 2 units. 1, 2, right? So moving up 2 units. So we're shifting the parent function f of x equal to x squared up by 2 units. And this is what we call a vertical shift. If you're subtracting, let's say g of x equal to x squared minus 2, then we would do vertical shift 2 units downward. Vertical shift from the parent function. Two units downward from f of x equal x squared and this is a basic vertical shift. And let's take a look at some of the horizontal shift. So as you can see, h of x could be written as f of x plus 2 because x squared is f of x. So since we're adding 2 to the entire function, so we're shifting up and down. Right, so adding 2 meaning shifting upward by 2 units. Also, let's say g of x equal to x minus 2 squared. If you sketch the graph, the parent function is x squared. So in the gray one, the black one is a g of x. So we're shifting the parent function 2 units to the right. Okay, so we come up with this g of x. So if you adding and subtracting a constant from the x value itself, then you're gonna have a horizontal shift. It's subtracting 2 meaning shifting to the right 2 units. Okay, if it's adding 2, let's say h of x equal to x plus 2 squared. That means we do a horizontal shift 2 units to the left. From parent function f of x equal to x squared. Okay, so it all comes with a different kind of transformation here. But generally speaking, we could do this. If you add in c to the f of x, meaning we will shift vertical shift c units up, subtract c from the f of x, and vertical shift c units down. If you subtract c from the x itself, so horizontal shift c units to the right, adding c to the x, horizontal shift c units to the left. So we have 4 different types of, if the constant was being added to x by itself, or subtract from the x, horizontal shift. If it is adding or subtracting constant from the entire function f of x, then we have vertical shift. So that's a major difference to distinguish the vertical shift from the horizontal shift. And some graph could be obtained from a combination of vertical shift and horizontal shift. Vertical and horizontal shift generate a family of functions, each with a same shape but with a different location in the plane, in a Cartesian plane. All right, so let's look at this. Okay, so use the graph of f of x equal x cubed to sketch the graph of each one of these. So first of all, let's find out what is the shift here. So basically subtracting 1 from x cubed, meaning so for part A, the transformation should be described as vertical shift 1 unit downward from f of x equal to x cubed. Okay, so that means x cubed is this. Then you just shift each one of these points on the function and shift it down 1 unit, and you actually generate a new, shift down here and then connect those 2 points. Just shift each point downward, get some points from the graph, and then you'll be able to get the graph for the g of x here. So every single point move down 1 unit. Okay, that's how it goes. Okay, and the second one, we have a combination of 2 transformations. First of all, we adding 2 to the x. That means first 2 being added to the x. So we're shifting the graph 2 units to the right. Now adding 2 units to the left. Okay, shifting. So horizontal shift 2 units to the left first. And secondly, we're adding 1, meaning we're shifting vertical shift 1 unit upward. Shift up 1 unit. Okay, so this combination of 2 transformations, horizontal shift and a vertical shift. So right here, first of all, we move all these 2 units to the right. So you're gonna get this. Let's go first 1, 2 right here. So you're gonna get this intermediate transformation first. move this one to the right 2 units. Get that, and we get this one first. Now you just shift all these points 1 unit upward, and that's how we get this transformation function. Alright, so connect it, and you get the transformation function based on this 2-step procedure. Okay, so that's how we use transform using the function notation to do the transformation here. So also here the order does not matter. Here we could do vertical shift 1 unit upward first, and then after that horizontal shift 2 units to left. So the order here does not matter. We can do either way. We can do vertical shift first and then horizontal shift, or we could do the horizontal shift first and after that have a vertical shift. So order does not matter in terms of the horizontal shift, and then order does not matter. Okay. Now, second type of transformation is what we call the refraction, refracting graphs. Okay, so let's look at refraction. So we have 2 types of refraction. Refraction about the x-axis. If you look at the refraction about the x-axis, you see with the same x values, y value are exactly the opposite. Okay, same x value, y value becomes opposite. Here's 1, here is -1. 1, -1. Okay, so this is essential component about the refraction about the x-axis. So keeping the same x value but y value become opposite according to this principle. So y value, you see, we put negative sign in front of x squared, so that will guarantee the y value becomes opposite. So this is how we form a mirror image about the x-axis. Okay. So refraction about x-axis, h of x becomes negative f of x. This will guarantee the y value become opposite. Same x value, and then opposite y value. If you look at the refraction about the x-axis, a typical graph like this, and refraction about the y-axis, the graph will turn into this. Okay. And then if you look at this graph, we're gonna have the same y value. So let's say same y value here, but the x value will become opposite. Okay. So with the same y value, this is negative x, this is x. Okay. So that's why when you see the function notation, h of x becomes f of negative x. Okay. So x value becomes opposite. And that's how we interpret the refraction in the y-axis. Now, let's look at this function f of x equal x to the 4th power, and this is a graph of it, right? This 4th-degree polynomial function, parent function of 4th-degree polynomial function. Each of the graph below is transformation of the graph, f, and then write equation for each of these functions. So we know that this is the graph for x to the 4th power. Okay. So first of all, I'll say it's going to be a refraction about the x-axis first, right? So you get this. All right. So refraction about the x-axis first, and then that means y value becomes opposite. And after that, we shift up 2 units. So all these points go up 2 units. So 2 steps of transformation. First step, refraction in the x-axis. Second step, shift up, vertical shift 2 units upward. So refraction about the x-axis, meaning y value becomes opposite. So first of all, g of x here should be negative x to the fourth. And then it's shift up 2 units, so adding 2 in the back. Okay, so that's how we come up with the transformation function. So this is first one here. Second one, again, this is our original graph. Now we could do a shift to the right 3 units. So shift to the right 3 units first. Get this. And after that, refraction about the x-axis. Okay. So 2-step transformation again. And here I'm doing the horizontal shift first. So shift to the right 3 units. 1, 2, 3. 3 units. And step 2, refraction about the x-axis. So the equations look like g of x okay, h of x, we're using h of x here. To the right 3 units, you do x minus, no, adding 3, no, subtract 3, shift to the right, subtract 3. And to the fourth, refraction about the x-axis and the y value become opposite, so put a negative sign in front of this. So you get a transformation function. Okay. According to this combination of the transformation here. Yep. And we're sketching the graph of function involving square root. You will make sure always domain is greater or equal to 0 or non-negative. Domain is non-negative. So here domains, for example, if you get negative radical x, then the domain must be x greater or equal to 0. If it's radical of negative x, then domain must be x less equal to 0, right? And domain of k of x is negative radical of x plus 2, then the domain must be x greater or equal to negative 2. And how we get this is very straightforward. If let's say last one, you want to make sure this is greater or equal to 0. So then subtract 2 from both sides of the equation. That means x must be greater or equal to negative 2. Yep, that's how we get this domain by solving the inequality here. And similarly, for the second one, negative x, you want to make sure negative x is greater or equal to 0. And when you multiply negative 1 from both sides of the equation, then we change the inequality side to the opposite. So x is less equal to 0. And that's how we get that. By solving this linear inequality, you'll be able to get the domain, proper domain for each different radical functions. Now, up to this point, we're talking about rigid transformation. Again, the graph, all these horizontal shift, vertical shift, refractions are rigid transformation because basic shape of the graph is unchanged. And this transformation only changes the position of the graph in the Cartesian system. And we also have non-rigid transformation, which have we call a distortion. Okay, so distortion is the key characteristics of the non-rigid transformation. So it will change the shape of the original graph. Now let's take a look at how the non-rigid transformation happens. So first type is vertical stretch or vertical shrink, vertical distortion. So this multiplies c to the function c times f of x, give us the vertical distortion. If the c when the c is greater than 1, then the vertical stretch then we have vertical stretch. When the c is between 0 and 1, then we call it vertical shrink. Okay, so that as you can see, when c is greater than 1, then the y value becomes much bigger. So see that it will become narrower, the graph will become narrower. That creates the vertical stretch. For example, let's say we have f of x like that. Now, when the c is, you multiply this function by, let's say, 3 times. Then for each given x values, now the y value is much bigger. So you're going to see something like this. 3 times as big, right? Instead of original value, the y value becomes 3 times as much. And this is f of x. And let's say this is g of x, which is 3 times f of x. Then we have a vertical stretch. Yep, that's where the vertical stretch happens. And also, if c is greater than 0, less than 1, let's say it becomes half of this function, then we'll have a vertical shrink, meaning it will become wider. The graph will become wider. For the same x value, now the y value will become use different color. Instead of having this the y value now will become half as much. So the screen graph will represent let's say h of x. H of x is half of f of x. Okay. And this is a horizontal, vertical shrink. Also, it's like horizontal stretch. Now, if you multiply c, so multiply c to the x, we're going to create a horizontal distortion. Times c of x. So the when transformation, when c is greater than 1, you get a horizontal shrink. And when c is between 0 and 1, we have horizontal stretch. So similarly, for example, let's say we have a f of x, given f of x is this graph. Okay, and this is f of x. if now it becomes f of 2x, so let's say g of x equal to f of 2x. So every time you have the same x value, now this x value become bigger. That means we're gonna have the graph will become this. And this is g of x equal to f of 2x. As you can see, it become the same x value here. And again, y value become much bigger. So become narrower. Narrower means horizontal shrink. And if you have the h of x, which is half of that, and then the graph will look like this. So it becomes horizontal stretch. Similarly, if h of x is f of half of x, so and this becomes horizontal stretch because the graph becomes much wider. Compare the graph of each function with the graph of f of x equal absolute value of x. First one, h of x equal 3 times absolute value of x. And we know that this definitely, we multiply the, and you can also write this h of x equal to 3 times f of x. So you multiply c to the, multiply constant to function itself, and we have a vertical shift, vertical distortion. So here, this is definitely vertical stretch. Okay. And second one, g of x just becomes 1/3 of f of x. So we know that this must be a vertical shrink. By using the function notation, it's a lot easier to figure out this non-rigid transformation here. So you look at first one, you see you get for the same x values, the y value becomes 3 times as much. That's why it becomes a much narrower graph, and much narrower graph indicates it's a vertical stretch, because this is narrower. And here we know this is vertical shrink. That tells us the same x values, the y value become 1/3 as much. So that's why you make it a lot wider graph, and a wider graph gives us a vertical shrink, right? Vertically it shrinks. It's like compressed to make it wider. Okay. So compressed effect. So that's why vertical shrink. Vertical, it's like vertical distance becomes shorter.